Moving along, we're up to 5, 1, 2. Stretching exponential functions. So here we are, we're back to exponential functions. They start with the function we should be somewhat familiar with, y equals x cubed. That's not a negative, that's just a tick mark going up, so don't be confused. So 0, 0, 1, 1, negative 1, negative 1, or 2, 8, negative 2, negative 8. If I just plug things in, there it is. So these are variations of this parent functions, and we need to know that a vertical stretch is the same thing as a horizontal compression. I'm going to demonstrate what I mean in a minute. So here's a 4. What does that mean? It means it's going to vertically stretch. It's going to go up faster, and so it's vertically stretched. Now look what happened horizontally. It's getting skinnier. That's a horizontal compression. So it's a horizontal compression by 4. It's a vertical stretch by 4. Now let's move on to, I'll do this one in green. Well, this has a little PEMDAS. What's 2 cubed? Well, that's 8x cubed. So this is bigger than this. So this is going to vertically stretch it even faster. So the y's go down faster, the y's go up faster. So that's a vertical stretch of 8. But it's also a horizontal compression of 8. Now we'll use purple. So 1/4 times 1/4 times 1/4 is actually 1/64 x cubed. Now what does that mean? It means it's going to go up a lot slower, so it's going to look like this and that. Probably wider than that, but not going to worry about that. So what happened? Well, that's a vertical compression by 64. And it's a horizontal stretch. See, a vertical compression, horizontal stretch, same thing. Horizontally, it's getting stretched, but vertically, it's getting compressed. It's not going up as fast. Move on to this. So, it says, consider this exponential function. That's a, that's b, that's our exponent. The parent function would then be f of x equals 1, because that's my a, my normal a, times 2 to the x power. Now I drew a little picture of it. How do I know that 0, 1 is exact? Well, if I put a 0 in there, 2 to the 0 power is 1, 1 times 1 is 1. So I know that's true. We talked about exponential growth, where if this is bigger than 1, it's going to grow. Now, with that being said, now my a is 4. So what does that mean? Well, it's very similar to this. See, rules don't change. That's a vertical stretch by 4, and that's a horizontal compression or shrink by 4. Well, what would that mean? Well, you would see very little difference here, very little difference here, but here you'd see it go up a little bit faster. What's this? Is it right 2 or left 2? Well, using our rules, even though it's in the exponent, that's going to be right 2. So I've moved this whole thing right 2 and just try to duplicate it. And now where's my y-intercept for this problem? Well, you got to use a little common sense. Anytime a point goes through the y-axis, we know that x is 0. For example, that might be 0, 4. That might be 0, negative 4. All I know is x is 0. So I put 0 in for x, so that gives me 4 times 2. 0 minus 2 is negative 2. Now you've got to use some algebra 2 here. That's the same thing as 4 times 1 over 2 squared, which is just 4 times 1/4, which is just 1. So my y-intercept for this would be 0, 1. All right, we're partway through this lesson. Hang in there a second. So this one I'm going to qualify as math just messing with you, seeing if you can remember some of your tricky algebra 2 skills. Watch this. Here's m of x. We just dealt with that. I just rewrote it on the board. Now, different instructions. It says write the equation of an exponential function in form h of x equals a times 2 to the x power. So similar to m of x. But then they say with y-intercept 0, 1. That's just saying let x be 0, y be 1. All right, what is this? That's y. So y equals 4 times, whoops, we don't know what a is. That's what they're having us find. A times 2 to the x power. Well, anything to the 0 power is 1. So that's just saying a is 1. So my answer would be right here. And they could give you a different y-intercept and you'd get a different a. But then they're going to ask you a tricky question. Is h of x, remember we just found it, 1 times 2 to the x, the same thing as m of x? At first glance, you're like, no. Well, you know, these math people want you to see this moment like, whoa, I didn't see that. The answer is yes. Now let me show it and prove it to you. But if you don't know this truth, then you don't really know what to do. So when the bases are the same and you're multiplying, you add the exponents. Here comes the trick. The trick is right here. I could rewrite that as 2 to the x times 2 to the negative 2 power. Because when the bases are the same, you're multiplying, you add the exponents. So that's times 4. Now I'm going to just forget about this for a second. What is this? Well, that's the same thing as 1/4. It's 2 squared flipped. What's 1/4 times 4? 1. So I get 1 times 2 to the x equals 1 times 2 to the x. And we go, holy cow, yes, they're the same. And you could actually type this in decimals, and just check it. You'll get the same graph. All right, let me pause it. Okay, so we're going to review this formula, but this formula has a little twist, and it's going to kind of shed light on why we're about to teach what's called logarithms. Don't panic, it's not that bad. Let's start with this. We know this formula is our investing formula. How much money in account? So they're saying, how much? So they want to know how much is going to be in there after 10 years. So we know that the time is 10. We'll fill that in a minute. But the initial investment is $2,100. 1 plus 6%, 0.06. And it's compounded annually. That means once a year. So n is 1, time is 10. So we're just going to put a 10 there. But okay, 2,100, 1.06 to the 10th power. Now we can do that with our calculator. If we just go 1.06, raise that to the 10th power, I get 1.79. I'm going to multiply that by 2,100. I get 3,760, $3,760, are my eyes working? And 78 cents. So not bad, okay? Made 1,700 bucks or so. Look at this problem. How long? Uh-oh, they're asking for t. Will it take into account to have 20,000? So now they're saying, okay, we want it to grow to 20,000. So they're telling us put 20,000 in for that. That's the value of the account after so much time. But if 4,000 is invested, so that's 4,000 invested at 7%, compounding quarterly, so that's 4 times a year. So that's 1 plus 0.07 for t. We're trying to find t. Now, I can't distribute this through because I don't know what this is, but I can divide this side by 4,000, divide that side by 4,000, so I get 5 equals 1.07 to the 4t power. And you're like, huh, how do I solve for t? Well, you're about to be introduced to logarithms, and without logarithms, we can't solve this. So that's the reason I'm showing you this. If you have your exponent stuck, your variable stuck in your exponent, you gotta know your logarithm rules. So that's why I'm going to start teaching you about logarithms. So give me a second. All right, let's tackle some of these log problems. So first of all, we got to bridge the gap between the world of the known to the world of the unknown. Now, some of you might already know this from maybe being introduced to it in Algebra 2, but I'm not going to take that chance. Here we go. This is an exponential equation. You guys are used to it. We would say 2 cubed is 8. Notice the base is a normal size number. The exponent is just cute and small. And then 8, the answer, is also normal size. Now, I'm going to convert that to a logarithm. Notice we got a 2 and an 8 and a 3. If I had students read this, I guarantee it, students would go log 2, 8, and this is where the change comes. This stuff we read left to right. This stuff we start here because that's my base. Notice it's written small. Things have changed. We start here. We go there. What's that? That's my exponent. How's it written? Normal size. And then we go here. So guess what we say when we read this? 2 cubed is 8. It's the same thing as this. It's just written as a logarithmic equation. So you're thinking, well, what's the value? You'll see. There's a whole world that gets opened up because of this world of logarithms. And you remember that last problem I showed you that we couldn't do? That's why we're being introduced to logs. Logs fixes that problem, but we're not quite there yet. So look at these three problems. Sometimes you'll see the instruction simplify, sometimes you'll say the instruction solve, sometimes you won't see anything. It's like, well, what do I do? Well, you got to remember there were 3 parts to an exponential equation. There's 3 parts to a logarithmic equation exactly like this, just written differently. And you just have to realize, well, what's the missing part? Well, the exponent is the missing part. Where do you start? With the base. Where do you go? Here. What does that mean? We're going to convert this to an exponential equation. So base, normal, exponent, small. There's my spot where my answer is. I never said that. That right there is my answer. And then that's 32. And on this one, you can use common sense. Like, go up the ladder. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So x is 5. Now, I'm going to show you one thing, though. It's a quote that I tell my students. Common bases, happy places. We're going to do this a little different. I'm going to rewrite this. I'm going to go, okay, I'm going to rewrite 32 as 2 to some power. Well, we already know it's 2 to the 5th. So these kind of cancel, and I say x is 5. Now you might say, I don't like that way. Well, that way is going to work for you on the more complex problems. Let's tackle this one. What's missing? Missing our exponent. Start here, go there, rewrite it. Base, exponent, here's my answer. 1 over 125. Now some of you guys can do this in your head, but I'm going to stick with the program. Common bases, happy places. So I'm going to convert that to 5 cubed. Notice I have common bases. And remember, if I have a negative exponent, I put it where it isn't, and I'm good. Well, if I put a positive exponent where it isn't, it turns negative. So that's what I'm going to do with this. I'm going to rewrite it, 5x, bring that up, and I get 5 to the negative third, and then these common bases disappear, and I can see x is negative 3. So this is negative 3. Because 5 to the negative third power equals 1 over 25. Now here's a little twist. It's like, wait a minute, there's no base. Well, I'm not going to bore you, but every time you type in numbers, your calculator uses base 10 numbers. Having said that, it's kind of like a square root of 49. There's missing things. There's a 1 there and there's a 2 there, and you just don't take the time to put them in there because it's assumed. Same thing here. If there's nothing there, it's a 10. And then you're off to the races because you can go, aha, 10 to some power equals 1,000. Now I know you could say x is 3, but I just want you to get in the rhythm. Common bases, happy places. I'm going to go 10 to the x, 10 to the third, that's what 1,000 is. Then the bases disappear and I can say x is 3. One more thing to show you. And we're done with this lesson.